The topic of this video is solving exponential growth and decay problems. Let's look at a problem. The half-life of carbon-14 is 5,730 plus or minus 40 years. For this problem, assume it is 5,730 years. If a piece of charcoal made from the wood of a tree shows only 64% of the carbon-14 expected in living matter, when did the tree die? Okay, so I'll admit, this is one of my favorite problems of the entire semester. The problem we're about to solve gives you an idea of how archaeologists use a process called carbon dating to determine how old an artifact is. I need to explain a little bit of chemistry, and then we'll solve this problem. First of all living things have radioactive matter in them, but it's not always harmful. For example, I am alive, and therefore I have radioactive carbon-14 within me. As long as I'm alive, the amount of carbon-14 will be maintained by my body. But as soon as I die, the carbon-14 begins to break down. This is true of all living matter, plants and animals. So if you want to determine how old something is that you find that happens to be dead, one thing that you can do is measure, based on its size, how much carbon-14 you would expect it to have if it was alive, and then compare that to the amount of carbon-14 it has now that it is dead. That can be expressed as a percent. That percent can determine how long ago the item died, and therefore determine the age of this particular item. Okay, now let's go ahead and solve this problem. We've got a piece of charcoal made from the wood of a tree. It's dead, and right now it has 64% of the carbon-14 we would expect it to have if it were alive. The question is, when did the tree die? In other words, how old is it? So we're going to solve this problem using the short way first. We're going to set up a table where we have time as our column on the left and amount as our column on the right. Time is going to be measured in years because that's what it says in the problem. And amount is going to be measured in percent because that's what it says in the problem. Okay, great. So let's go ahead and solve this problem. We know that at the moment that the tree died, which is the moment that the clock starts, time 0, that it had 100% of its carbon-14, because as long as it's alive, the carbon-14 is maintained. And we know that the moment it dies, a half year later, then it will have half of that value. So when 5,730 years go by, then the amount of carbon-14 it will have is 50. And when another 5,730 years go by, so we'll add this with our calculators, 5730 plus 5730, that's 11,460, then it will be half again, which will be 25% of the original amount at the moment of death. Okay, so now we're ready to try and solve this problem. When it was 64%, how long ago was it? Well, sadly, 64 does not show up in our table, which means we cannot use the short way to solve this problem. We cannot simply observe a pattern to solve this problem. So that's going to force us to do this the long way, which is to use the exponential law equation. But let's get some useful information from our table before we do. So the first thing we want to determine is the adder A and the divider D. So we can see that as we move down the chart, we're adding 5,730 over and over and over. So A is equal to 5730. And if we look here, this is decay, 100%, then only 50%, then 25%. So what's the pattern? What do you have to do to 100 to turn it into 50? Well, you have to divide it by 2, so the divider D is equal to 2. Our equation, our exponential law equation, says A of t is equal to A naught e to the kt. All right, let's start plugging in what we know. Well, we know A naught. A naught is the amount when the time is 0. When the time is 0, the amount is 100. K will come from a formula. K is equal to the natural log of 1 over d, all divided by A. So in this particular case, k is equal to the natural log of 1/2 all divided by 5730. So when we need k later on in our solution, we have it right here and we'll be able to plug in. All right, now we're ready to answer the question. We find this tree, we measure the amount as a percent, and we find that it's 64%. So 64 goes right here in the amount space, and we get 64 equals 100 e to the kt. The question says when. So we're looking for t, solve for t. When what you are trying to solve for is up in the exponent, use the converter. So we want to use the converter, but we have to get rid of the 100 first. So divide by 100 on both sides. And I'm out of room, so I'm going to clear some space over here. So then we're going to have 0.64 equals e to the kt. We've got base, exponent, and argument. Let's put it in our converter. Base is e, exponent is kt, argument is 0.64. All right, matching up the colors and shapes on the other side, we get log base e of 0.64 equals kt. And log base e is a natural log. So the natural log of 1.64 is equal to kt. Divide both sides by k. And we get that our exact answer t equals the natural log of 0.64 over k. Now we know what k equals. We have a formula for k. So let's go ahead and put that in our problem. So we have the natural log of 0.64 over the natural log of 1/2 over 5730. So we've got a fraction within a fraction, but we don't have to panic. We remember the rule that when you divide fractions, you keep, change, flip. So keep the natural log of 0.64 exactly as it is, change the division into multiplication, and flip this fraction over. So the 5730 will go to the top, the natural log of 1/2 will go to the bottom. Now, it just so happens that 1/2 is the same as the decimal 0.5, and this fraction right here, this item, natural log of 0.64, can be written as a fraction over 1, and this allows us to put these things together. So, to multiply two fractions, you just multiply across. Natural log of 0.64 times 5730 would be written 5730 natural log of 0.64. Anything times 1 is itself, and I'm going to replace this 1/2 with the decimal version, which is 0.5. So this is my exact answer, 5730 times the natural log of 0.64, all divided by the natural log of 0.5. Now all I have to do is put that in my calculator, and I'll get myself an answer. So here we go. First, 5730 times the natural log of 0.64, close parentheses, enter. I get negative 2557.225098. Divide by natural log of 0.5, close parentheses on the argument, enter. 3689. So 3, 6, 8, 9, and the calculator's got some decimals here, 295,967. So now we go to the rounding instructions in the problem. I didn't happen to provide any, but the web software that you were using to solve a problem like this will give you instructions. Let's just make something up. Let's assume that it asks us to round to the nearest 100 years. No, actually, we'll go a little more than that. Let's see here. Plus or minus 40. Maybe 100 is good. Let's go to the nearest 100 years. So that means we want to look at that particular decimal place. So this is approximately 3,700 years. That is an old artifact. 3,700 years old. All right, so we've done something pretty neat today. We've learned how archaeologists use carbon dating to determine how old artifacts are.